All right. Good evening, everyone. Thank you for letting us present our quantum chemistry research. So today we would like to unveil our research on a novel method for the characterization of conformational isomers and extensions of Python-based Hartree-Fock methods. My name is Rishab Ghosh.
I'm Shashank Kadavidi.
And I'm Jaden.
So a key aspect of our research is the Schrödinger equation, and this is probably one of the most fundamental equations in quantum physics, quantum mechanics, anything. It's a differential equation that solves for the wave function of an electron in an atom, and it allows for calculations of electron energies and probability distributions. And as you can see here, the Hamiltonian and the eigen energy. And it's very useful for calculating energies, but it gets extremely complex for multi-electron systems due to electron correlation energy.
Self-consistent field methods, or SCF methods, are computational approaches applied to approximate Schrödinger's equation solutions. These techniques modulate the electron wave function by means of recursive approximations. Iteratively improving this wave function will help us to converge to an atomic energy stability. We essentially begin with an initial estimate for the electron distribution, compute the consequent potential, then solve the Schrödinger equation to obtain a fresh electron distribution. This method is repeated until the findings show convergence by stopping noticeable changes. Essentially, there's not too much of a big difference from each subsequent iteration. And each of the several SCF techniques is intended for various degrees of precision and efficiency. The Hartree-Fock approach is one well-known example, since it approximates the interactions between electrons in a form that can be solved more readily, therefore simplifying the many electron issue. Accurate modeling of chemical systems and property prediction depend on an awareness of and application of SCF techniques. The Hartree-Fock method applies SCF techniques to determine the electron wave function by calculating the Schrödinger equation using two key matrices, the Fock matrix and the density matrix. This allows us to calculate the energy of multi-electron atoms with good accuracy. A key component of SCF techniques is our model of the initial wave function guess. This is where basis sets come into play. Basis sets are essentially combinations of multiple functions that model the electron orbitals. They enable us more effectively to approximate the wave function. Each of the several basis sets has advantages as well as trade-offs. Slater-type orbitals, for example, are computationally slower but more precise. Conversely, Gaussian-type orbitals, or GTO for sure, compute far faster but are less precise. GTOs are hence a common choice in many different applications. One often used example is the cc-pVDZ basis set, which balances computational efficiency and precision by aggregating 3 GTO basis sets.
All right, so the project goals of our group is number one, to compute molecular energies using PySCF, which is a self-consistent field library in Python. And we want to use this to reduce the time and resources needed to calculate and compute these molecular energies, as calculating such energies is extremely important for the drug industry when discovering new drugs. So in reducing the time and resources needed, it's more efficiently helping the industry with drug discovery. And preliminarily, we have tested alkanes and different hydrocarbons such as ethane and propane, which are all straight chain alkanes. Again, using the Hartree-Fock method and the cc-pVDZ basis set. Our second goal is to tabulate the data and create a scatter plot for runtime and SCF energy. And this will be done through regressions used for approximations and prediction purposes. And then lastly, we want to repeat the process for halo compounds, oxo compounds, etc., which will help test the accuracy and precision of our program. And then this again is going to be in preparation for a quantum computing collaboration with one of Dr. McMahon's groups. So specifically, we have an isomers paper, and the paper's goals is to use XYZ geometries of the various isomers from the computational chemistry comparison and benchmark database to compute the ground state energies of various molecular forms, which are basically the isomers. And then overall, we want to find trends between the structure of molecules and the resulting energies that we calculate.
In our research, we applied the Hartree-Fock process using the Python library pyscf, which automates various self-consistent field methods for us. Our initial focus was on calculating the energies of different isomers. We used pyscf to calculate and compare the molecular energies of several hydrocarbons. As you can see to the table on the right, Hartree-Fock generally succeeded in ranking different isomers by their energies. However, it occasionally fell short in finer instances when compared with actual data from the CCBDB database. A notable example is the comparison between 1-butene, cis-2-butene, and trans-2-butene. We observed that trans-2-butene had a higher energy than cis-2-butene due to its greater hydrogen-hydrogen repulsions. This indicates that Hartree-Fock can effectively identify and account for hydrogen-hydrogen repulsions within a molecule. To achieve even more precise results, especially on a finer energy scale, we can employ newer and more accurate computational methods like DFT, or density functional theory, with exchange correlation functions. DFT provides a better understanding of the correlations between electron orbitals compared to standard Hartree-Fock methods. This marks the core of our research, which we will expand on later in this presentation. Here's essentially a summary of our methodology for the Monte Carlo. Given the ground state conformer of a straight chain alkane, we treat the XYZ geometry as a tree structure. Here's how the Monte Carlo process is used to generate new trial states. We begin by performing a breadth-first search, or BFS, from a starting carbon atom. This search helps us systematically explore the possible geometries by adding atoms to the central carbon atom. As we add atoms in the BFS order, we ensure that the distances between atoms remain consistent with those in the ground state conformer. This maintains the structural integrity of the molecule while exploring new configurations. For each trial state generated, we use pyscf to calculate the MP2, or Møller-Plesset perturbation theory energy. We then compile these energies into a histogram to analyze the distribution and find optimal configurations. By using this Monte Carlo approach, we can efficiently explore a wide range of molecular geometries and identify energetically favorable conformations.
And here's our implementation for the Monte Carlo. And as you can see, we have some pseudocode here, if anyone would like to try and understand or comprehend how we implemented everything. And so, as mentioned in the previous slide, we created a function to generate the isomers. And this Monte Carlo trial function took into account bond angle, torsional strain, and bond length to create different conformations. And then it iterated over the function 1,000 times to create 1,000 different conformations. And then eventually, for each one, it outputted the converged SCF energy, again, using the Møller-Plesset perturbation theory calculations. And so after we compiled all 1,000 energies, we calculated the median of the converged SCF energies and compared that with a ground state energy for the molecule. And we're hoping to obtain a value within chemical accuracy of 1 kilocalorie per mole. And finally, after all our Monte Carlo analysis and calculations, we use geometric clustering algorithms, and where we align the centroids of the different isomers for each straight chain alkane with the ground state conformer, and ignoring rotations and reflections of a conformer. And the clusters indicate the major conformations a molecule will tend towards. As you can see, there's higher concentration in the center over here, and that'll kind of indicate what the molecule will tend to conform as.
Here's a quick conclusion, as well as kind of how our project is going to unfold in the future. So first of all, our proposed methodology has been successfully implemented and has demonstrated its effectiveness. However, there are several areas where we aim to expand and enhance our approach. We are currently focused on extending our methodology to handle larger molecules with more conformers. This will help us better understand complex systems and their behavior. We are actively seeking ways to speed up SCF methods and Hamiltonian evaluations. Our previous research indicates that runtime increases approximately quadratically with system size, so finding efficient solutions is crucial. We plan to extend our work to include larger straight-chain alkanes. In the future, we aim to include other types of structures, such as branched or cyclic molecules, to kind of broaden the scope of our study. Also, instead of fixing atom distances, we intend to use force fields like MM2, MM3, or MM4 to adjust distances dynamically. This would allow for more flexible and realistic molecular modeling. We also plan to explore frequency decomposition using Fourier analysis, which could provide additional insights into the vibrational properties of the molecules.
Another project we are working on is PySCF UI, a tool for researchers that provides an easy and intuitive way to perform self-consistent field calculations and thermodynamic analysis. Yeah, okay, so our current UI takes in XYZ geometries of molecules and is able to calculate and display the molecular energies like that on the right-hand side. And the goal of our tool is to simplify running PySCF calculations and quickly see trends with automatically generated graphs. So on the left-hand side is our interface for choosing parameters for the computation. And on the right-hand side, we have metrics for runtime and the buttons to export the data. Again, on the left-hand side, we have our common molecule geometry database. And on the right is our selection of basis sets for SCF calculations. And here on the left, we have more examples. We have examples of some of the computed values for 1-butene. And on the right is a 3D and 2D visual of 1-butene. Another feature of our UI is our trend finder, which automatically scans for trends in the data computed. So our UI allows you to input multiple molecules, and our trend finder will brute force the data and try to find trends and display it. And this will help speed up research and just make it research overall more efficient. So some of the goals for our UI is to extend our UI to be able to run on GPUs, as a lot of this is computation heavy, and being able to run on GPUs would just save a lot of time. Another thing is to implement geometry optimization. We'd also like to add post-Hartree-Fock methods, and we would also like to add more molecule geometries to our database from the QM9 dataset.
On the behalf of our group, I'd like to extend our heartfelt gratitude to those who have supported and contributed to this research. Dr. McMahon, our advisor, whose guidance was invaluable through the research process. Dr. New for providing crucial advice on advancing our work with post-Hartree-Fock methods and achieving our goals. ASDRP as a whole for offering us the facilities and resources to conduct our research, as well as past group members whom, without their dedicated efforts and past contributions, this research would not have been possible.
Thank you very much. And if anyone has any questions, feel free to ask.